So good afternoon, everybody. My name is Antonio Castelo, technology expert at Epic, and I want to welcome you to this new Epic member, new product release, online meeting where different companies, Epic members, present the new developments or new solutions in the market. So it's a very good opportunity to learn what is new related to different photonics technologies. And just a few words about Epic. Epic is this group of 800 companies, photonics related, and the consortium is taking care of the sustainability of the photonics business in Europe, helping the different members to learn about the new markets, to understand new applications, find new opportunities of collaboration, find new partnerships, new business opportunities as well. Big thank you to all the members for supporting the activities of the consortium, and in particular the 6-1 that will speak today and will present today their new developments. And as I mentioned, a few words about the benefits for all the attendees that are not part of the consortium yet. So these are the benefits that we offer to our members. So we support in understanding new markets, both with market reports and also with the support of different mentors. We also support in other activities related with the company, like human resources, investment and financial activities. And we also support in these activities like this one that are technological request related and also networking related. So as I mentioned, supporting all the members find new partners, new collaborations, and new business opportunities. So if you are an Epic member and you have any of these needs, feel free to contact us for discussing how can we help. If you are new and you are interested in knowing more, also feel free to contact to discuss how can we help and with the way we can collaborate with your company. And related with the networking activities, we organize different physical and online meetings like this one. In the next month, in May, we will have quite a lot of different online meetings related with marketing topics, also technological discussions, also related with careers and human resources activities. And one interesting discussion on May the 7th about the impact of US tariffs. That is the discussion that happens every time we talk with a member. So I think it's a good opportunity to put things in common and discuss the impact for the European photonics community, and perhaps trying to find solutions or at least share ideas and ways of overcome potential problems. And we continue with our physical meetings, of course. The main focus that will be in the next weeks in Laser World of Photonics. We also have a panel session at Display Week in the US, and also we have an activity related with AR, MR, VR at the More Photonics technology meeting. But of course, we are going to be in Munich, so I encourage all the members that are going to visit the show or participate in the show as exhibitors to check the different activities that we will have there. We have an exhibitor breakfast, marketing related activities, human resources, sustainability, also technological meetings that I will mention a little bit later. So I encourage you to go to our website. And in the particular case of the integrated photonics, there is a specific application stage that we take the 4 days of the meeting with different presentations of companies related with PICs, both in terms of the technology and the applications. So again, I encourage you to check in the website what's happening there. And finally, we will be back in September with a technology meeting on industrial laser processes, organizing Italy, and the Tech Watch that we normally have at W3 Fair. And as I mentioned, the meetings that we will have in Munich related more with the technology. So we will have these 4 specific sessions. On June 24, a specific meeting on defense to discuss about potential collaboration between members, also understand what are the needs and the technologies that will be more needed in the future. This is one topic that we discussed several times in the last weeks, also in the general meeting. How can we help members or support members in finding opportunities in defense? So I think this is a good starting point from the discussion we had in Barcelona a couple of weeks ago. We will have also a tech session focusing quantum technologies within the World Quantum Hall in Munich. Also another technology meeting on innovative optics to talk about materials and components. And finally, another technology workshop about laser micromachining applications. So for all the companies involved in ultrafast lasers, applications development and components could be a good point of contact also for discussing. And we'll have some interesting integrators there to talk about the needs and potential collaboration with them. And we can go with the first presentation. This is the agenda that we have for today. So it's a quite good variety of different technologies. So we will talk about passivation with Comptek. We will talk about different connectors, fiber optic connectors with Diamond, also laser processing of materials with LASEA, the PICS topic that I mentioned, presented by LIGENTEC, also quantum PDKs with wave photonics, and of course, hyperspectral solutions with Nireos. So I would like to introduce our first speaker today, that is Elias Tsiatas, is Sales Business Development Director and Comptek Solutions, and he's going to present the new Controx TM Late 16. So Elias, going to stop sharing my screen, and the floor is yours.
Okay. So good afternoon to everybody.
You can put in full screen mode, that will be
Yes.
yeah, perfect.
So now we go. So good afternoon, everybody. So I present here Comptek Solutions, and we're going to talk about our newest equipment. First of all, a short company introduction. So our main technology is surface engineering, atomic level surface engineering, in order to boost the performance and the efficiency of semiconductor devices that they are based on 3-5 compound materials. We are 27 people. Our target industries is lasers, but also micro LEDs, power, RF, quantum, and also substrate solutions. And in order to execute our technology, we use several ultra-high vacuum reactors and also ISO 5 clean room capabilities in our state-of-the-art lab. And addition to that, we have also characterization capabilities, especially for the opto semiconductors. Our solution and business model is passivation to develop passivation technology for wafers and laser bars. And finally, we transfer the technology through equipment and license. We are founded in 2017, a spin-off from the University of Turku based in Finland. Our technology itself that you're going to find in the equipment has to do with the bottleneck in the industry, that is for the 3-5 compound materials, that is typically the amorphous oxide that you can find always on the interfaces, on the surfaces of the semiconductor material. So what we do is we apply our Controx, the technology that creates a stable, high quality crystalline oxide that is very well organized on atomic level, and creates a new interface upon the semiconductor material and before the dielectric deposition, or before the mirror coating, if we speak about lasers. The structures or the architectures where you can apply our technology are sidewalls, mesa sidewalls, then of course the laser facets, also interfaces you can find in transistors, also substrates. And we speak about different combinations of compound materials, gallium arsenide, indium phosphide, gallium antimonide, but also gallium nitride, and so on and so on. Also, by the way, important to know that also aluminum, where you can find aluminum, is also a material that we can handle with our technology. If I go now to details to the system we want to introduce today, that is dedicated to laser bar facet passivation. You can find the two chambers, the processing chamber, where you have the plasma source, RF plasma source. Then you have you have the heating system where you control the temperature, of course. Then we use spectrometers to monitor the processes, and the e-beam evaporator. Then in the other chamber, the load lock chamber, there you can find the stacking jigs. So we have up to 8 pieces. Then the barcode reader, the degassing preheating system, And the transfer arms that they are also automated, and we control, of course, the whole process, the two chambers using the electronic cabinet that comes with the whole package. I would like to emphasize 5 main characteristics of this system that makes it very interesting for the laser industry. Of course, the first one is the passivation quality that is very comparable to the high quality industry standards like zinc selenide, but at a remarkable value to cost ratio. So we speak about a clear competitiveness in terms of finance. And the other thing is the multi-process chamber makes the whole system very compact because you do all 3 processes, the cleaning, the passivation, and the sealing within the same ultra-high vacuum system. Then we offer high throughput. Of course, it depends quite much on the size of the laser bar, but we can go up from the laser bars we have seen in the industry, we can go up to 1,800 laser bars per day. Please remember that we have the 8 stacking jigs in the system, and this, of course, helps to have a high throughput. But from the feedback from customers, I would say one of the most important is the laser facet stability, because the passivated facets now, they are so stable that they remain in a very high quality for days, I would say even for weeks. So we remove the time pressure and we improve the flexibility when the customer design his plan. He's going to plan the mirror coding process. And finally, with the same machine, we can run multiple recipes for the various wavelength laser materials. If we speak now about some data from that system, first I would like to present the lifetime tests. Here you can see on the right, comparison comes from a customer between the standard process they have in their production, the reference, and after 1,500 hours, you can compare it with laser bars that they are passivated with our Quantrox technology, and you can see that here we improve significantly the lifetime of the laser bar. One other parameter important is the uniformity. Here you see an example where gallium arsenide is cleaned. We have a 6-to-6 reconstruction across the whole sample area. And then if you monitor, we have reduced the oxygen significantly together with a carbon. They are on the bottom of this graph. But at the same time, we have a very nice one-to-one ratio almost between gallium and arsenide all over the clean surface that you can see on the top of the graph. And finally, the thermal distribution. We have software, of course, to track the distribution, the temperature distribution in the laser bars. In this test, we have used 210 stacked silicon spacers, and we have reached a very nice uniformity, I would say, both in X and Y axles. And we want, of course, we know that there is room for further improvement through some optimizations that we're going to do. And as an overview, I would say that the Quantrox quality is high, similar at least to the zinc selenide well-known system in the industry. But at the same time, our Quantrox offers a high throughput for mass production purposes. And also very remarkable in the discussions with customers we have noticed, of course, is the cost of ownership. That it's competitive against the existing methods. Finally, a review of the business model is that the customers will send us the laser bars. We do a proof of concept where we demonstrate the efficiency of the technology, and then we optimize the process for a technology transfer to mass production that includes not only equipment, but also the annual technical services and some accessories. And of course, by doing this, there is also freedom to operate because it's the license to to use the Controx technology. And I want to close the presentation by a very short video of the system. So thank you very much for your attention.
Thank you, Elias. Thank you very much. So we have time for questions, so you can raise your hand and make your question directly to Elias. We already have one question from YouTube. Elias, can smaller components like wafer-based micro-sized wave-guide facets also be treated?
Yes, but let's say the size, exactly this equipment is optimized only for laser bar facets. So the technology itself can be applied and will be applied on wafers, different size of wafers, from 2 inches up to 8 inches. But then you need another kind of equipment.
Mm-hmm. So perhaps they can contact you, perhaps for further discussion.
Exactly.
About this specific component.
Exactly. Okay. I mean, if it's about small size wafers, yes, then there is another solution. Yeah.
So for the person in YouTube, you can contact Elias and Comptek directly. You can discuss this question directly with them. And I have also a doubt regarding potential contamination, because you use the chamber for the different processes, so cleaning, passivation. How do you solve potential issues with contamination between one process and the other?
Exactly. For the time being, the material we use in the chamber is gallium arsenide, and we have cases where the bars, they have also aluminum. So, I mean, all the cases, basically, they have aluminum.
Okay.
For indium phosphide, we are going to have a similar system, but we are going to, let's say, update and use some hardware parts in order to, because in indium phosphide, we need other level, for example, it's a different material, so we need other level of temperatures, and so on. And the same is valid also for gallium antimonide, if I understood your question right.
Yeah. That's good. Okay, so if there is no more questions, thank you very much, Elias, for presentation, and very good luck with this new product in your markets. And we will be in touch about potential new applications. So let's discuss in the next weeks.
Thank you.
And we can move to our next presentation. We pass to the fiber optical connectors by Diamond. So I want to introduce Daniel Giampà, Business Development and Product Manager from Space Defense Harsh Environments. So Daniel, the floor is yours.
Yes, thank you very much. Hello everyone. I'm going to share the presentation.
Yes, you're going to present the mini ABIM.
It's basically the meeting adapter of the mini ABIM.
Okay.
Yeah.
Okay.
So is it in full screen?
Everything good. Yeah, everything good.
Okay. Okay. So yeah, let's go. I quickly present you an overview about Diamond, for the ones who don't know about what we do and who we are. So we are located in the south of Switzerland. It's our headquarters, and we have two subsidiaries, one in the US in Boston and one in Germany in Stuttgart. We are about 250 employees in the headquarters, and then in the two locations about 50. We are a privately owned company. We have then some worldwide representatives in various countries, Europe and Asia. What we do, we manufacture fiber optical connectors and solutions. So not only maybe the connector itself, but solution that can be the female part, the mating part, connector with a coupler, with a splitter, and so on. We are a vertically integrated company, so we try to buy the raw material and from our suppliers and do all the production in house. And we have some clean rooms of various class, ISO 6, ISO 7, and ISO 5, of about 800 square meters. So the ISO 7, we already had it since 10 or 15 years. We built recently the lower class clean rooms for semiconductor and space market. And now I'm going to talk you about a product that is related to high power and space. We have called it PST vacuum for high power and space. So the name of the product is just PST, but I will explain you later what we're talking about. A quick introduction. For the one who doesn't know, we have technology from our connectors that are developed for high power. So power solution, we call them Diamond PS. They are, originally we developed them for operation on ground, so on atmospheric conditions, telecom, and for Raman amplifiers and lasers, but everything that is on ground. Recently, let's say, demand from the market, where always more and more high power is requested, but not only on the ground, but more and more as well in space, so not in an atmospheric condition. As we have already our mini Avin connector, that is a connector qualified from ESA according to the ESCC guidelines 3420 and so on. We basically, we show you here, developed a mating adapter that is not only, let's say, mechanical and geometrically and technically features are the same, because we already had a mini Avin adapter, so it's basically the female part for our connector. In this case, it's the PST, so we called it Power Solution Thermal, with two slightly modification of the connector. Otherwise, as said, the material is as well the same. What is special about it? We tested it in some special conditions, so under a vacuum condition with a certain temperature, certain hour, specific time, and at up to 6 watt. So the normal, let's say, operational power for this connection between mating adapter and connector is standardly about 300 milliwatts, and in this case, for the space, as said, for the PST, we reached up to 6 watt, and we have tested it in our laboratory up to 100 hours. And we some future milestones. We would like it to qualify this PST mating adapter according to the ESA guidelines, as we have already the connector qualified, because until now we did our test in-house following the same test process as ESA guidelines, but it is not yet ESA qualified product. And another milestone we want to reach is up, instead of 6 watt of operational power, go up to 16 watt. So this is another milestone we would like to reach. And yeah, basically I summarized all the two key points I wanted to share with you. And yeah, this is my presentation.
Perfect, Daniel. Thank you very much. Again,
Welcome.
we have time for questions. You mentioned about the qualification by ESA, but it doesn't mean that it can be used for space applications, right? So it means that perhaps ESA requires this kind of certification to use in their projects, but other potential projects can use your solution right now.
Yeah, they can use our solution right now, even in space, because it has been tested in vacuum conditions, so it can be used. But because it follows the test process from ESA, but not qualification from ESA. So this is the little bit the difference.
Yeah. And regarding the new powers that you have in mind, do you think that you will finish with the 16 watts, or do you see that it's going to be evolution even in higher and higher powers that you will need to take care in the future?
This is a good question, yeah, because until now we have been requested to have a power that is more than 6 watt. So let's say around 10 watts. So we have not been requested yet, I don't know, 30 watt or 50 watt, but it's something we could see after the test results of the 16 watt, yeah.
Okay, so you are not there, but you see evolution of requiring higher and higher powers in the last years.
Yeah, we think that it can be requirement will grow in this market, yeah.
Good. And this kind of similar product, can it be used for another application that is no space, or this is really focused in this particular application?
We released the product with the mindset to focus to the space market, but as it is a product that has been qualified under tested under a vacuum condition, it can be used even in other applications that require that have a vacuum condition, but can be something else. Yes.
Okay. Interesting. We have a question from Alter Technology.
Yes.
I don't know if you can do it directly, William, or if you are not with the microphone.
Yeah, I see the question.
Yeah, it's can you confirm if the connector is suitable for SMPM fiber?
Yes, it's suitable for single mode and PM fiber until now, so no multi-mode fiber. But for those two, yes.
Okay. And we have another question in YouTube. Can you say something about damping loss in dB?
Damping loss, we have made a quality test report about it. So to be more precise, I would like to maybe send this document to be sure. What I have in mind should be about insertion loss, maybe about 0.4, 0.6 dB. And but yeah, to be sure, I would like to check and maybe send this document, yeah, to the contact.
Okay, so Daniel showed the details, contact details. So perhaps I see that is Thomas in YouTube. You can check directly with him later on.
Yeah. Okay. Thank you.
Yeah. So Daniel, I think there is no more questions here. So thank you so much for the presentation and for showing us your new product.
Thanks to you. Thank you.
And we can move to our next speaker. So we move now from optical fibers to laser processing of materials. It's a pleasure to introduce Jean-Christophe Wauters, luxury market manager at the company LASEA, and he's going to present the new Concept 1 OP.
Yeah, thank you, Antonio. Yeah, hello everyone. So I'm going to share my screen. Yeah.
Perfect.
Okay, thank you. So yeah, my name is Jean-Christophe and I work for the company LASEA. So LASEA, we are a laser micromachining machines manufacturer. So we are located in Belgium and we have different subsidiaries. I will show them to you later in the presentation. So my presentation today is about the 1OP. So 1OP, it means one operation. So it means how to machine one part in one operation. But I'm going to explain that to you more in details. So first, a short introduction to LASEA. So LASEA, we are a Belgian company, as I told you, a group. We have 8,500 square meters of production on 6 different sites. We have 3,000 machines installed all over the world. We have around 120 patents. We have machines on 5 continents, 50 years of experience. So it's quite a lot in the laser industry. We have 15 application engineers, so that's the team where they make the feasibility test for customers. So when a customer wants to buy a machine, he wants always start the project by organizing a test. So that's the team who are organizing those tests for customers. So altogether in the company, we are 200, a bit less than 200 employees, and we have an annual growth of around 30%. So just for the story, I started the company, it was a little bit less than 10 years ago, and we were 45 at that time. So it's a big growth. So just to summarize how we are organized all over the world. So I'm located in Belgium, so in Liège, so that's where we have the headquarters. And then we also have a production facility in France, in Marnay, so that's close to Besançon, and that's the company Laser Cheval. So we took over the company Laser Cheval a few years ago. Now they are a member of the LASEA group. We also have another company in Belgium, in Mons, called Comptek. We have a subsidiary in Bordeaux, so called LASEA France. We have also a subsidiary in San Diego, in California, and in Switzerland for the watch industry in Biel. So that's where we are located all over the world. So we have different markets. As Antonio told you, I'm responsible for luxury, but we also have electronics and medtech. So luxury, it's mainly for LASEA, the watch industry, Swiss watch industry, but not only. We also have machines in the watch industry in Japan and in other countries in Europe. So electronics is more Asia, not only, but more Asia, and also medtech more in the US. But again, not only. Research, so it means that we also have machines in the universities and R&D centers. So let's talk about the 1OP. So as I'm responsible for the watch industry, I'm going to take an example of a part made for the watch by the watchmakers. So it's typical a part that you can find in a movement of a watch. So how they do today, the watchmaker, they start with the raw material. Can be different material like brass or stainless steel or titanium, and they want to produce this final part that you see here. So we had a lot of discussions with the watchmakers in the past years, and they explained us how they are producing this type of parts today. So I'm not going to go into details about how they are producing those parts today or before today, because it's not about laser, but it's just to show that there are many operations, like different types of machines, like milling, wire EDM, gear cutting, decoration machines. So that's only an example, but every watchmaker has a different way to produce the parts. So what I want to show here is that you have many machines and also many manual operations, like loading, unloading the parts from one machine to the other, go to the cleaning machine, and then put the parts again in the next machine. So it's quite complex. It works very well because they are doing that for more than 100 years, but it's quite complex. So our target with our laser machines, micromachining laser machines, was to make it simple, more simple for them. So I will continue with this example of the part I showed in the beginning. So with laser micromachining, you have different types of applications. So first, as you probably all know, when you machine a part with a laser, you will always have a taper. So for gear, for example, in a watch movement, of course, it's not possible to have a taper because the gear will not work. So for that, we developed a system that we call LS Precess. So it's a precision head, which will allow the laser to machine the material without taper. So in this example, you see that the part where you don't where the taper is not acceptable. So that's the drilling and also the cutting. As I mentioned before, it's very important that you don't have this taper. So how we do that? We use a laser, femtosecond laser. We place different modules that we develop ourselves in the beam path. So it's the LS shape to shape the beam, LS precess to avoid this taper, then LS polar to modify the polarization, LS view to be able to view the part through the scanning head, and then the scanning head itself. So you see here, I'm going to use the laser pointer. You see here how the laser beam look like after the laser source. Then you go into the laser, the LS shape. Then you will make it, for example, bigger, and then you go through the LS shape. So the LS shape will transform this shape, this round shape of the laser beam to like a donut. And it's because we give this movement, as you see on the right side of the slide, you can see that the laser beam is moving to compensate the taper. So the advantage is that we don't have any taper anymore, but we have like a donut instead of a single spot. So because of that, if you want to machine, if you want to engrave, for example, you will have this donut. So it means that you will have a problem. You cannot engrave like a normal laser machine without this precision head. So you cannot engrave because of this donut. You can also not create the chamfering. You can also not make the engraving and texturing because of that. So, and the decoration, the same. So what we did, we decided to have this LS precess, but we can bypass it. So it means that, as you can see here, we don't have this donut anymore because we have a bypass. So it means that inside the precision head, we can move the laser beam to another path, and then you don't have this donut anymore. And then you have a normal machine, and that's what we call 1OP, because in one single machine you can either cut or drill without taper, but you can also make the decoration, engraving, chamfering, engraving, everything. So it means you need only one single machine to machine this complete part. And that's what we call 1OP, one operation. So as a summary, this is how the watch industry is producing the parts today. And we make it simple. We use this machine that we call LS4P machine. And then you only have the raw material at the entrance of the machine, and then you push the button, you push start button, and then you will take the parts finished out of the machine. So it means you have only loading, unloading, one operation, only laser, only one machine, and then you can save time. You can increase your flexibility because you don't need a special tool. It's only a file, DXF file. You reduce your footprint if you compare all the machines you have on the left side comparing to one single laser machine. You reduce your overall investment because you only buy one machine and not maybe 4 or 5 machines. You reduce, of course, your energy consumption, and especially with laser because the consumption is very low, and you also reduce your consumable costs. So it's really to make it simple and flexible for the watchmaker. So to finish my presentation, I just wanted to show you some examples of real parts, just to show you the quality that we can reach. So again, we start with a raw material, and then at the exit of the machine, you have this type of part. We just had a polishing, a cleaning and polishing operation after machining with laser, but it's really the part which comes out of the machine after the laser. It's really the quality that we can reach, and that's what the watchmakers need. So yeah, that's my presentation. I don't know if you have any question, and I hope it was clear and that you enjoyed.
Thank you, Jean-Christophe. So, yeah, we have time for questions. I will start with one, and it's related the potential number of lasers that you need inside the machine. Depending on the task, do you think that in some cases you will need to integrate two different lasers, or the idea is to have only one laser source and then play with the different modules and components?
Yeah. So a few years ago, you're right, we had to integrate two different lasers in the machine. So it means that we had one femtosecond laser, for example, for the cutting, and we also had the nanosecond laser for example, polishing with a laser, or also to create some decoration, some texture on the parts. But today, because the laser can have either femtosecond or nanoseconds in the same laser source, we can only use one single laser. So it's one femtosecond laser, but with an option called nano switch. You can switch the pulse duration from femto to nano, and the machine is standard. It's a green wavelength, but we can also have two wavelengths. So it means green and infrared. If the customer needs, we can also have the two wavelengths. Yeah.
Yeah, that was my other question about wavelengths in case different materials can be used.
Yeah, but standard it's a green femtosecond laser.
Okay, very good. I don't know if there is any other question. Well, if not, thank you very much, Jean-Christophe. I guess you're in Munich, presenting also this kind of solution. So I encourage everybody interested in laser processing of materials to pass by also LASEA booth to talk about potential needs.
Of course, yeah, they are welcome. And maybe just one point I can add, it's that we also created a total cost of ownership with this solution, and we also compared I would say the conventional machining with the laser, and we can compare how much it costs to produce one part with laser compared to the conventional machining. We have a complete study, and we can also share that with the customers.
Okay, that's a good point.
Yeah.
Thank you very much, Jean-Christophe.
Yeah, thank you.
So we can move to our next speaker. So we are now going to talk now about integrated circuits. So it's a pleasure to have Henry Francis, application engineer in LIGENTEC, to talk new applications for the thin film lithium niobate modulator. So Henry, the floor is yours.
Thanks, Antonio. I'll just share my screen. You can see it okay?
Everything good, yes.
Okay, perfect. So yeah, as you said, today I'm going to talk about how we can unlock the potential of silicon nitride photonic integrated circuits by adding active components onto the chip. So I'll just talk a little bit about who we are as a company. So we are a European photonic integrated circuits company with a global outreach. So we're based, as I said, in Europe, and we serve to many countries across the globe. We started here in Switzerland, in Lausanne. This is where our company was founded. We've now grown to have a facility in France, in Corbeil, and now we've just as of last year, we have incorporated in Belgium as well to take advantage of some of the talent that we see coming out of Belgium. We're a company based, well, it says 70 photonic enthusiasts. I think we're now up to 80 photonic enthusiasts. We are all highly trained, highly skilled, and very enthusiastic about working on photonic integrated circuits. So what is it exactly that we do? We have the best-in-class integrated passive silicon nitride. So we have incredibly low loss silicon nitride. We have 3 different technologies, which I'll talk about briefly, and an extensive PDK, so you can use our chips and our design services. So we have 2 fabrication lines where you can fabricate your photonic integrated circuits. We have one which is for our standard technology. So here we have a number of different technologies installed. And these can be used to do very high volume manufacturing. We also use it for doing pilot line studies and niche quantities. And we have an offering where you can join a multi-project wafer run so that you can take advantage of this standardized industrialized process, but with a lower cost and a lower entry barrier. So that's one platform, and the other one we have is our R&D line. So here, if you need something specialized, if you need something away from the standard, then it's possible to use our R&D line to look at new concepts, to understand new technologies and new materials. And the benefit here is once we've developed something on our R&D line, we can then transfer it to the 200mm line, where we're able to offer, again, higher volume and a very standardized process. So silicon nitride is a very nice platform for photonic integrated circuits because you can work at a lot of different wavelengths. It's transparent anywhere from 400 nanometers up to 3 or 4 micron. There's high power handling, and it can be very low loss. So what we offer on our standard platform is 3 different thicknesses, and these are aimed at different wavelengths. So with your 800 nanometer platform, we predominantly aim at the C band and for doing nonlinear photonics. For the 350, this is aimed at the C band and the O band, so 1310 nanometers up to 1550. And here we have incredibly low loss. So this is a platform that is optimized for linear passive circuitry. And then we have the AN 150, so the 150 nano platform. And this is aimed at visible light applications. And with each of these processes, we then add on additional modules. So you have your silicon nitride waveguide, where your light is guided through this material. We can then heat the waveguide to change the phase, or we can open the cladding if you want to have a different material integrated onto the waveguide. And we can do a partial etch of the waveguide, so you have polarization control. So now we have these thicknesses, we have these modules, and then to use this, we have an extensive PDK, which includes splitters, combiners, edge couplers. Everything has been tested over many runs using wafer level testing to ensure long-term stability and reproducibility of the circuit itself. So this is a very nice platform. It's existed for a very long time. But the problem with silicon nitride is you can't do fast modulation, you can't do detection, and you can't do amplification of light. So how are we working to solve these problems? First of all, we are integrating lithium niobate on top of the silicon nitride. So lithium niobate is an emerging technology, which at the moment seems to have a huge amount of energy behind it, because we can see that you can modulate your light up to 100 gigahertz, and this has huge potential in datacom, in telecom, also in space and defense, and RF over fiber technologies. So what we've done is we've integrated this new material onto our standard silicon nitride platform. The benefit here is you're able to take a platform which has been established for many years, which we've worked on to develop a very reproducible and very standard stable platform, and we've added on this emerging technology on top of the silicon nitride to add functionality. So here the benefit is that you now have very high speed modulators which are integrated onto our standard silicon nitride platform. So we take our advanced technology, we add on a new innovation, and this gives us this integrated circuit where you have both materials integrated into one chip. This figure here just shows you how the mode looks when the light is guided by the silicon nitride, but the majority of the mode sits inside the lithium niobate, so you can do very high speed modulation. So what's available, what's on offer from us? So as I said, we have this very stable silicon nitride platform now with high performance electro-optic modulators in a robust, reproducible and reliable PDK. And how can you get access to this? So there's 2 different ways. One is through dedicated runs. So you can come to us with your design, we can fabricate it for you, and this can start at any time. We also are aware that often a lower price point is needed, and for this reason we have multi-project wafer runs. Here these have fixed deadlines, the next one being the 15th of May, so this is coming up quite soon. If you want to join this run, there is still space available, so please contact us. And the next multi-project wafer run will be in September of this year. Just to look at another integration concept we have. So that was obviously for modulation, but we also have photodiodes integrated onto the same platform. So here you can then, not only can you modulate your light, but you can also detect your light on chip. So in this method, we use micro-transfer printing. So we take the photodiode from a wafer and we print it onto the waveguide. This has very high alignment accuracy. We can have incredibly high throughput, so you can have many of these PDs put onto your chip, and it reduces the effort required for packaging. This is, again, the benefit of this platform is that we can use our standard silicon nitride, and we can add photodiodes on top of the silicon nitride. Again, for key dates, so for dedicated runs, this can start any time, and our next multi-project wafer run is starting in October. So that's all I've got to say. I'll just finish on this slide, just to give an overview of our standard platform and our latest product developments, which include high-speed, high-performance electro-optic modulators and micro-transfer printed photodiodes.
Thank you very
Thanks.
much. Thank you very much, Henry. So we have again time for questions. I have perhaps one related to the potential for medical applications, because you mentioned several points that could be interested for somebody developing, for example, a wearable device or a device for biomedical. Do you see that is one of the markets that could benefit apart from telecom datacom that you already mentioned? Do you see any other potential interest in other industries?
Yeah, so I mentioned datacom and telecom and microwave photonics. For biosensing or for medical applications, again, it's similar that you need to have these very high quality, robust devices that can be used many times, and our platform is designed for that. So we do see there is an application space for that.
Very good. I don't know if there is any other question. Well, if not, thank you again, Henry, and please take note of the dates that Henry mentioned in case you are interested in this process, so you can reach LIGENTEC for being part of this fabrication.
Thanks a lot.
Thank you, Henry. So we can move to our next speaker. So we move now to Quantum PDK. So we have James Lee, CEO at the company Wave Photonics. So James, you can show us what do you have.
Okay, thank you. Slides. Can you all see?
Yeah, everything good.
Okay, fantastic. Yeah, so hi, I'm Jamie. I'm one of the co-founders of Wave Photonics. I'll give you a quick introduction to the company and then focus on the product we released recently, which is a quantum-focused PDK. So we are primarily focused on being able to quickly design fabrication-tolerant PDKs. So this is targeted both at fabs and PIC designers, but the core capability is this ability to learn about a fabrication process and generate a PDK very quickly. So for foundries, this can fit in as an additional PDK offering, but it's also the turnaround time is fast enough that it can form part of the process optimization. And then we also, coming soon, because we're dealing with so many of our own designs, we've had to build infrastructure to cope with that. And we realized this may be a useful tool for foundries in terms of distributing and managing PDKs. For PIC designers, the offering is very similar, whether it's targeted a custom application or they're doing dedicated wafer runs. But also we realize it makes sense to open up our kind of PDK development pipeline to external users. So that includes, for example, doing wafer scale characterization or access to ADKs or packaging templates. So this maybe for this audience is a bit basic, but really the problem we're setting out to try and solve is to help reduce the number of iterations that are needed to get a functioning PIC product. And this is especially true for the applications where you need to design your PDKs from scratch. So most of the foundries have their own PDKs. They're improving all the time, but they're primarily designed around the telecoms bands, because today that's where the largest portion of the market is. And that means if you want to work away from the telecoms bands, you need to do the development from scratch. So our core technology is this pipeline for PDK development. And what I mean by that is we start by characterizing the fabrication process. So we get some information from the foundry, and we also run like a test run to get some information on our dedicated training patterns. And that forms a training data set for a fabrication process model. So that means for a given foundry, we can know for any target design, how is that design likely to come out when it's manufactured? And more importantly, what's the space of ways that that design can come out when it's manufactured? So that then sits as a layer within an optimizer that lets us optimize a component design for some target specifications for the range of ways that we expect that to come out when it's manufactured. And because we can do that massively in parallel, it means we can take a sort of preset library of components and optimize them all in one go. So from there, that gives you a library of like GDS files that can be usable. But to sort of make it easier, we integrate that with several of the EDA tools, and this list is growing over time. So what that means is from our website, you can download a package that just plugs into any one of these tools, along with documentation, assembly design kits, tutorials, and then all of the PDKs have like detailed version histories. And then lastly, we close the loop with wafer scale measurement. We need statistical data on these components. So we have a very an automated but very focused testing system to get a high volume of data. So the nice thing is it works. So here are two examples. One is comparing a simple MMI design to the foundry design. And in this case, you see a 4 times performance improvement and a 4 times like size reduction. But maybe the more important comparison is comparing this design to, or comparing these designs to designs done via kind of conventional inverse design. And so what we see here, this is on the right-hand side, is comparison between inverse design and our design approach. Measured data on the same chips, on the same wafers. The devices are right next to each other. And what we see is about a factor of 2 improvement in the loss. We're much closer to our target ratio, a fraction of a percent versus several percent. And then crucially, for the same amount of process variation, we see about a factor of 2 reduction in the performance variation. So putting that all together into the product release for today, this is our Sync PDK. So it's a PDK developed on a 200 nanometer silicon nitride process. We picked 200 nanometers because it means that it facilitates wavelengths right from the blue-green into the telecom C-band. So we kind of co-developed this process with Cornerstone and used the rapid turnaround time to help optimize the process parameters there. So this PDK allows on the same process to address 33 individual wavelengths targeted at the transition lines of a range of quantum systems, and this will be available on Cornerstone's visible wavelength silicon nitride process, which has its first MPW rates later this year. we also did the same thing for the telecoms bands across 4 different fabrication processes. And then lastly, all of these PDKs are compatible with our packaging templates, which means for any wavelength you choose or any process you choose, the input and output couplings are optimized for the relevant fiber modes and fiber arrays, and can be packaged in a kind of simple predefined way with Alta and using Senko's fiber arrays. So thank you. That's it. Let's take any questions.
Thank you very much, James. We have again time for any question or comment. I have perhaps one question about the training process, perhaps for a new user. Do you support in the starting process of using your PDKs to integrate in the process? How do you used to do with your customers?
So do you mean bringing up a new PDK on a foundry process, or giving access to the PDK to a designer?
No, in the first case,
Yeah. So in general, we take whatever information the foundry can provide and build that into like version 1, and then we do a kind of test run where we have some trial some trial photonic components and the training patterns that we take CM images of, and then that's used as kind of data to feedback on the next version of the PDK. So it's something that kind of continuously improves over time, but what we've seen is you just get a very significant increase from just that iteration 1.
Yeah, very good. I don't know if there is any other comment or question. Well, if not, thank you very much, James, and for showing all your capabilities in this field.
Thank you.
So thank you for being here this afternoon. And we finished today with Fabrizio Preda. She's the CEO of the company Nireos, and we are going to move now to hyperspectral cameras. So Fabrizio, the floor is yours.
Thank you, Antonio.
Sorry that we are a little bit later than expected, but I hope that you can have time.
No problem for me. I will be quick enough, I hope.
No problem.
I will share the screen with you in full mode. Can you see it?
Not yet. Now it's good. Yes.
Perfect. Okay. So thank you for the introduction, Antonio. Again, I'm Fabrizio. I'm the CEO of Nireos, and today I'm going to talk about our new hyperspectral imaging system. It's a hyperspectral camera. We call it HERA, and has the uniqueness, say, of measuring over very broad spectral coverage from the visible to the infrared in a single measurement. So just a few words on Nireos. Nireos is a company. We are based in Milan, north part of the city. We were born almost 7 years ago as a spin-off company of Politecnico di Milano University. And in these years, we've been growing. We are now up to 15 employees with more than 15 distributors worldwide. And we basically develop and manufacture solutions for spectroscopy, so devices for spectroscopy, such as hyperspectral cameras, spectrometers, detectors, and interferometers for Fourier transform spectroscopy. So in this talk, I will talk about hyperspectral imaging in particular. So what's spectral imaging first? I think that many of you already know. Just to clarify, here in the slide, you can see the difference between RGB imaging, multispectral, and hyperspectral. The differentiation between these 3 areas is the number of bands that the device can measure. So RGB is the simplest one, of course. Every camera is an RGB system that we're used to, so it measures 3 bands in the red, green, blue. A multispectral system refers to a system capable of measuring a discrete set of bands. Typically, this is something between 5 and 20, whereas hyperspectral means the capability of measuring the continuous spectrum for each and every pixel of the image. So many more bands, hundreds of bands. And so we are going to focus today on hyperspectral. So there are many different ways and companies producing hyperspectral images. Some of them rely on the so-called dispersive approach. So they follow the suggestions by this guy, Sir Isaac Newton, who discovered that the light is made of different colors, the white light. And so these devices are based on gratings or prisms, such as common spectrometers based on gratings that everyone knows. But we have decided not to follow the suggestions of this guy, rather to follow the suggestion of this other guy, Fourier. So all our hyperspectral system, they work with a Fourier transform approach. This is the schematic of how Fourier transform approach works. This is depicted with a conventional and easy schematic with a Michelson interferometer. The idea for measuring the spectrum of light with this approach is to use an interferometer to create two replicas of the light. The two replicas of the light have a delay which is scanned, and by measuring the intensity signal as a function of the variable delay between the two replicas, one can measure this interferogram pattern, which is the autocorrelation of the light. And by performing the Fourier transform of this signal, you get the spectrum of the light. Now, these years we have been developing another specific interferometer. So we do not use a Michelson interferometer. We use our own interferometer. We call it Gemini. It is based on birefringence, and with respect to Michelson's interferometer, is much more compact and robust. So this allows us to work down in the UV region, visible region, and not only in the infrared, as common FTIR are limited nowadays. So this is the interferometer, highly stable, reproducible, and accurate. That's a picture of the commercial device. We call it Gemini. So the Gemini is at the basis of our devices, either spectrometers or hyperspectral cameras. So the concept is the following, as I was mentioning before. You have an interferometer. It creates two replicas of the light. They impinge on a detector, which measures the interferograms, and the Fourier transform gives you the spectrum. So this is a spectrometer. So this is the product we have, in which we couple the Gemini interferometer with a single pixel element to provide a super broad spectral coverage from 400 to 4.5 micron wavelength. It's a spectrometer, is an FT, not FTIR, because it works down in the visible or UV, so it's an FT-UV-Vis IR, if you want. It employs the Gemini interferometer. So this is a single pixel spectrometer. But now, what happens if instead of single pixel photodiode, we employ an imaging lens or objective and a 2D sensor? Then we can parallelize the measurements of the spectra for each and every pixel of the sensor, so that each and every pixel of the sensor, like a CMOS, can measure the interferogram, and then performing one Fourier transform for each and every pixel of the sensor, you get your spectrum for each and every pixel. That is the hyperspectral data cube. So the sensor can be of any kind, can be a CMOS, CCD, InGaAs, whatever sensor you want. And so you can develop a hyperspectral system based on this technology. That's something we have already done by selecting already some sensors to be integrated in our commercial hyperspectral systems. So we coupled Gemini with the lens and the sensor. So we did develop a hyperspectral camera, the Hera V-Near, with a silicon sensor. Then we have a model from 900 to 1.7 based on an InGaAs sensor. Based on an extended InGaAs, we have the extended SWIR camera up to 2.2 microns. And then we have brand new Hera V-SWIR using the new Sony sensor, the IMX990, which is capable of measuring the full range 400 to 1.7 in a single scan. So that's pretty revolutionary product. Nowadays, people that want to measure from 400 to 1.7, they need to use two different cameras and then try to stitch together spectra obtained from different devices. While here you have a single device, single sensor, single scan, so everything is much simpler. These are the main features of the camera. So it has a very high spatial and spectral resolution. The spatial resolution is simply given by the sensor, the lens, and the spectral resolution is given by the interferometer. It's a static approach, so you need to scan the camera while not moving anything else. This is not so typical in hyperspectral imaging. So in some applications, this might be convenient. It has a very high optical throughput. So again, the Fourier transform allows you to avoid using slits or gratings. So you have a very high light throughput, enabling low light illumination conditions or fluorescence measurements as well. And it has a variable spectral resolution depending on the, it can be varied by a software basically. The camera is suitable for remote sensing, macro imaging by just applying a macro lens for higher spatial resolution, and even more, you can couple the camera with any commercial microscope. And so you can upgrade your microscope into a hyperspectral microscope if you want to do hyperspectral imaging in microscopy. I will show you now an example of application where we used successfully this sphere combination of spectra in breast cancer detection. So this is a big project and big application we've been involved with in the last period. The goal is to characterize ex vivo tumoral specimens right after surgery in order to give the surgeon a prompt quantitative answer during the operation. So the surgeon can have a really fast answer during the operation without waiting 2-3 days from the response for the anatomopathologist. So this can speed up and improve the process of operations. So in this example, I'm going to show you some real measurements with it. So this is us working with a camera right in front of a surgery room in the hospital for breast cancer. The sample is this one. So this is just an RGB image of the specimen. So this is a tissue extracted by the surgeon and cut in half to expose the tumor that was inside. The tumor is here where the yellow arrow is. Of course, by an RGB image, the tumor is basically not distinguishable from other parts of the tissue. But if you compare the RGB on the left with the hyperspectral on the right, this is the hyperspectral at a selected wavelength only, you can see that you have a much higher contrast. And here you can see clearly the two tumoral masses here. So by performing hyperspectral imaging, you can collect many spectra in reflectance in this case over such a broad range. And you can differentiate between fatty region, for example, from cancerous tissue. And the capability of measuring not only the infrared, but also the visible was essential to be able to discriminate tumoral tissues from some other tissues, typically fibrosis tissue that were otherwise not recognizable and distinguishable from the tumor. So this was essential. And thanks to that, we developed some models based on some spectral angle algorithm to automatically segment the image and to give the surgeon a prompt answer. So on the left, you can see the result of the algorithm applied on the 20-second measurement time with the camera right after surgery compared with the H&E stained tissue from the anatomopathology department obtained after 2 days. And you can see that the match is pretty impressive between the two measurements. So this to demonstrate, this application, the capability of the device. Of course, this was just an example. The device is now being employed in a huge variety of applications from agriculture. For example, you can measure chlorophyll absorption and color of leaves in the visible and conjugate this information with the water content, for example, in the infrared, or for cultural heritage, for pigment identification, for solar and material science, either in remote sensing or microscopy for doing quality control. For example, you can map the band gap of your material. You can check the thickness of layers deposited on top of the different silicon wafers, of course, or in microscopy, if you want to really map your material and optimize the process for growing the next generation material for solar cells, such as silicon and perovskite tandem solar cells. Then microplastics, plastics, food inspection, microscopy. So many applications are unlocked thanks to this technology. Of course, depending on the application, the different spectral ranges might be more or less applicable or helpful, of course. So that's the conclusion of my presentation. I presented you a novel hyperspectral technology, and more specifically, a device based on this technology that allows you to measure over a broad spectral range, 400 to 1.7 micron, with a great spatial and spectral resolution and very high light throughput. And the system, as I showed you, is really super versatile and can be coupled also with microscopes. So with that, I hope to manage to be on time, and I thank you all for your attention.
Thank you very much, Fabrizio. So again, we have time for questions for our last speaker today. I have perhaps one question about, well, all the users of hyperspectral cameras are complaining about the amount of data, how to process all the data they receive from the camera. So how do you manage even increasing the wavelength range? Is this user adjustable resolution, spectral resolution, also a way to control the number of data in regions that you don't need so much information?
Yeah, that's for sure a hot point in hyperspectral imaging in general. So the amount of data is huge. And data can be like also 1 gigabyte, one measurement.
Yeah.
Half a gigabyte, 1 gigabyte. Of course, the cameras that we have are really high. They bring a lot of information, especially this broader model. Controlling the resolution is a way to control also the data size. So if you have applications that do not require a super high resolution, then you can anytime lower the resolution by your software, so the measurement is faster and the data size is lower. So you can always adapt the spectral resolution and the data size depending on the application. Yeah.
Okay. We have a question in YouTube. I'm not sure if it's if I do it well. Is what's the wavelength resolution in delta lambda lambda? I'm not sure if you understand the question.
The wavelength resolution.
Wavelength resolution in delta lambda lambda.
So I think it's delta lambda over lambda, maybe.
Could be.
Maybe I can try to answer. Then of course available for further details.
Yes.
So for example, to give you a number, the resolution at 400, so in the blue, is as good as 1 nanometer approximately. So it's 1 over 400, the delta lambda over lambda.
Okay. Yeah, I think this is the question.
So the resolution being based on a Fourier transform approach is constant as a function of energy. And therefore, as a function of lambda, it increases. That's why delta lambda over lambda is a constant.
Yeah. And I see that there was another question for a previous speaker, but I will put it later on. I don't know if there is any other question for Fabrizio. If not, yeah, Thomas in YouTube mentioned that that was the question. Okay, so thank you very much, Fabrizio, and we are reaching the end of the meeting today. So thank you to all the speakers for the time and for presenting your solutions. Best of luck with the new products in the next months, and we are in touch also to well, find new opportunities. We expect to help also from Epic side. So Elias, Daniel, Jean-Christophe, Henry, James, and Fabrizio, thank you very much for your presentations today. And yeah, thank you everybody for being here, and I hope to see you next time in a future Epic event. Thank you and good afternoon, everybody.
Thank you.
Bye-bye.
Bye-bye.
Thank you. Bye-bye.